Number 10 of chapter 13 from Knight's Physics for Scientists and Engineers, fourth edition, investigates the magnitude of the change in the free fall acceleration due to ascent up something like a mountain. So, I don't know, 10,000 feet or so. So let me draw a silly little pimple on planet Earth. Totally unrealistic because no mountain is that high. And let's say you're up here with a very sensitive instrument. This is a person for measuring the strength of G. And such an instrument, I believe, is called a gravimeter. I'm not sure of the pronunciation. Probably depends on who you ask, kind of like nuclear and nuclear. And well, why don't we just develop this formula from the beginning? It's a good reminder. I'll draw a little arrow to indicate the gravitational force on this person. And we have two expressions for that force. We know that if we take the number of kilograms from which the person is made, the mass of the person, number of kilograms times the number of newtons per kilogram in the gravitational field, right, the strength of the gravitational field, that's one way of calculating force or converting mass into force in a gravitational field. But we also know from Newton's law of gravity that if their mass is little m and the mass of the planet or moon is big M or Death Star, then we can use this formula, for the strength of the gravitational force between them. So it's inversely proportional to the square of the distance between their centers. That's the center of the person and the center of the Earth, which is not actually just the radius of the planet, since they've got this little extra boost from the mountain. So here's the radius of the planet. I'll just use capital R. And then this extra little distance here, I'll call it H, which is really the altitude. Altitude is how high you are above the surface of the Earth. So their total distance, if you look here, would be the radius of the Earth plus that extra little bit. So little r, distance from center to center, would be radius of the Earth plus the altitude. And you'll notice that the little m's cancel. And if we were evaluating the strength of the G field at the surface, then I could go ahead and plug in the radius of the planet. Because if you're standing on the surface, then your distance to the center basically is the radius of the planet. But here it's little r, which I can write as big R plus altitude. Square that. Now, if you actually plug in the radius of the Earth, so if we were talking about the strength of the G field, not at the top of the mountain, the first videos for this class were filmed in spring of 2019, and I made some stupid jokes at the time. When I coughed in the video, I said something like, "Oh, coronavirus," and now I actually had coronavirus, and that's why I'm coughing. I'm fine now. Just a residual cough. So if you did evaluate this, where your distance is just the radius, you would actually find a value close to 9.83 meters per second. And I'm going to put a little sub-zero there, G naught. And that, just for this problem, that's going to mean the strength of the G field at the surface of the Earth. And you may be wondering, why is it not 9.81? Well, remember, the Earth is turning. And as a result, the free fall acceleration that you feel on the surface is a little bit less than it would be otherwise. It's kind of like you're being flung outwards. That's really a topic for chapter 8. We looked at problems like that, so I won't dwell on that now. But just know that the spinning of the Earth causes the effective G field to be a little bit less than this. That's where that 9.81 comes from that you measured in Tracker. But I'm going to use this value for the G field at the surface of the Earth if the Earth were not spinning. And now, in this problem, we can see that the strength of the G field depends on your altitude. As your altitude increases, the numerator increases, and that means that the overall fraction or this quantity would decrease. So the higher you go, the lower becomes the strength of the G field. We could even say that G depends on H. It's a function of H. And what they told us here was the value of G at the top of the mountain, and we're supposed to solve for H. So it's like we're given the radius of the Earth. Of course, we know big G. We know the mass of the Earth, excuse me, And we're also told what the strength of the G field is at the top of this mountain. And we're supposed to solve for the height. So I'll just remind you, big G, not an easy number to measure. Very difficult to measure that number. Newton, what is it? Newton meters squared per kilogram squared. It's not important for you to know those units really. And then the mass of the Earth, I might have to look that up, but if I recall, it's 5.97. Yeah, that sounds right. 10 to the 24th kilograms. And you know what? If you look this value up in the book, that third digit, that third significant digit, I believe is different from the one you'll find if you consult Wikipedia. And I'm assuming that Wikipedia's is more accurate because those scientific articles are always being updated. I think that's an 8 maybe in Wikipedia. And that's why if you use this formula to calculate the surface gravitational acceleration, you'll get a slightly different number than 9.83. I forget if it's 9.82 or I think it is. It comes out different than 9.83. And I think the book it's 9.83 because they're using, now, you know, I forget. You can check it if you'd like, but if you plug in this number, which is the mass given by the book for planet Earth, you'll get a different value, I think. Yeah, I think that's when you get 9.82. So it's like, well, where does this 9.83 come from? If you go to Wikipedia and look up the mass of the Earth there and plug that mass in, I think you do get 9.83. In any case, we're told that the strength of the G field is 0.0075 meters per second squared less than it is at the surface. So let me add a couple zeros there. So minus 0.0075. I got 4 decimal places there. And oh, there we go, 4 there. I need those extra zeros to be consistent with, you know, the rule for adding and subtracting numbers with decimal places, decimal points. And that would bring us down to, oops. Okay, 9.8225 meters per second. So what we could do now is figure out how high we are to produce, or how high you must be to produce this G field. So that's one way to do it. I'm going to go back and do this a different way. That's a little more fun. But let's solve this for little, actually, we're solving it for little h. Yeah, so I'll multiply on both sides by this denominator. So I've got G, little g times big R plus little h squared equals big G times big M. And let's see here. Couldn't I do this? That's a big G, big M over little g. I'd have to take the square root. And then I could just chop off the plus h and put that. Oh, what am I doing here? Making this more complicated than it needs to be. This is big R plus little h. And now I'm solving for little h, right? Okay. Okay, minus big R. And let's see if I can do this all at once in my calculadora. So I've got the value of big G. I would multiply by the mass of the Earth, 5.97, 10 to the 24th. And then I divide by the value of G at the top of this mountain, 9.8225, hit equals, take the square root. And now I subtract the radius of the Earth. Now this whole thing's a little contrived because our answer is coming out with all these sig figs, and we're not even going to use a value for Earth's radius that's accurate to that many digits. Hang on one second. Okay, here's the problem I'm running into. The value that they want us to use here is 6.37 times 10 to the 6th meters. But that number is less than, excuse me, it's greater than the number that just came out of the calculator, which means I would get a negative value for height. So what have I done wrong here? The issue is that I'm only using this number to 3 sig figs, and that's no good. Yeah, in fact, often it's written as 6,400 kilometers. So your solutions manual did it a clever way, which is actually better. because it'll avoid this problem. So if I go back here, excuse me, they wrote this as the G at the observatory, because the premise of the problem is you're at some observatory that's up at the mountains, let's say. And if you look here, the G at the surface would be big G, big M over radius of the Earth squared. So let's see if we can extract that or find that within here. G at any altitude is, and I'll do this, inside the parentheses, excuse me, inside the parentheses here, I'm going to factor out the radius of the Earth. So let me put this as a bracket, and I've got big R times 1 plus H over R. See what I just did there? If you distribute big R, you've got R plus H, which is correct. And the reason we're doing that is now I can pull the big R out of the brackets. Remember, when you square a product, you have to square both factors. So I can write this as G big M over, I've now pulled out the big R squared, and I have 1 plus H over R squared. And the reason for doing that is now we can identify this as the value of the free fall acceleration at the surface of the Earth. That was the reason for this clever little device of factoring out the R squared. So we can say that G at any height, any altitude, excuse me, would be G naught, that's the surface acceleration, over 1 plus H over R squared. And now let's solve this. Let's solve this for H. I'm really sorry about the coughing here. So I'll just call this G now instead of G of H. G times 1 plus H over R squared equals G naught. So in other words, 1 plus H over R would be G naught over G square rooted. I think I'm doing this right. And that means H would be root G naught over G, all of that minus 1 times R. All right, you can check my algebra there, but the advantage of doing it that way now is we only have to enter R once. And I'm at a loss for how to explain that clearly at the moment, but hopefully you can see that that eliminates the difficulty I ran into over here. Okay, so we're told that the, so let me put in the 9.83. The free fall acceleration at this observatory was the 9.83 minus 0.0075. And then we multiply by the radius of the Earth, which I'll just round to 6,000. I think it's 370 is a pretty good number. Kilometers. Okay. So 9.83 divided by 9.8225 equals, then I hit the square root button, subtract 1, multiply that by 6,370 kilometers. Kilometers go in, that means kilometers come out, and the altitude there is 2.4. I'll go ahead and put, excuse me, 2.43 kilometers, which is what, like a mile and a half? So, well, this would be 2,400 meters. So close to 10,000 feet, approaching, what is that, like 8,000 or 9,000 feet? That's like the top of a fairly tall mountain. Okay, so this algebraic method definitely superior to the first method I was trying. And I want to expand on this. I'm out of white paper, so back to the legal pad. Let's look at this expression. I can say that G at any height is G naught times, and I'll use a negative exponent this time, 1 plus H over R to the negative 2. And now I'm going to use something called the binomial approximation, which is very useful. Some of you might really appreciate knowing this. Many of you will see this again. And here it is. If you have some quantity X, which is considerably less than 1, so let's say it's a 50th or 100th, and you take the quantity 1 plus X and raise it to the nth power, that's roughly just 1 plus the power times your small quantity X. And I use this all the time. It just shows up a lot. There are many problems where this ends up being useful. And this is one of them, because you'll notice right here, if the altitude is much less than the radius of the Earth, which it was, 2.4 kilometers is nothing compared to 6,400 kilometers. That means the ratio of the two is much less than 1. Right? The two less thans mean like super less than. So this satisfies the requirement of being much less than 1. So this quantity h over r is like x, or it plays the role of x, and the power n here is -2. So I'm going to show you an example that is not this problem. Suppose you wanted to know the cube root of a number like 1.0007, and you didn't have a calculator with a cube root button. Now, why would you find yourself in that situation? We all have calculators now with many more features than the cube root button, but I can write this as 1 plus 7/10,000ths, right? This is the same as 1.0007, and I'm raising it to the 1/3 power. So here, my x is that small number 0.0007, and my power n is 1/3. So the cube root of 1.0007 using the binomial approximation should be basically 1, or very close to 1 plus n, the power 1/3, times x, which is 0.0007. And that you can almost do in your head, or you can approximate in your head. So let's see here. 0.0007 divided by 3, and I add that to 1. And I find that the cube root should be roughly 1.00023. And I'll add a couple threes for good measure. All right. Now let's actually get a more exact expression for the cube root of 1.0007. I think I have a cube root button in here. There it is. Shift, arrow. So I'll say versus 1. Oh, that's terrible. What did I do wrong? 1.0021. There's only 2 zeros. Let me try that again. 1.0007. Oh, I did x cubed. Pfft, silly. Okay. Is there a cube root button? Yes, I missed it. 1.0007 cube root. There it is. Versus 1.000233. Look at that. If you round to that digit, that 7 turns the 2 into a 3. It comes out the same. So kind of remarkable that it's so accurate with really just 2 terms. You may, if you've taken calculus 2, you may recognize that what I'm actually doing is a power series. I've really just taken the first 2 terms from a Taylor series. I believe it's Taylor series. Yeah. And if we had included more terms, it would be, the agreement would be even better. So this is a really useful approximation to know, the binomial approximation. And let's now apply it to this formula. So I can say that 1 plus h over r to the -2, sorry, that's 1 plus, is roughly equal to 1 plus, well, my power is now -2, and my x is h over r. See that? Which is just 1 minus 2h over r. And so this factor, 1 plus h over r to the -2, that factor appears in my expression here. Such inefficient use of paper here. So that means g is equal to g naught times 1 minus 2h over r. Now, if I go ahead and distribute the g naught, that's g naught minus 2h over r times g naught. And that means that the change, which I'll call delta g, the decrease or the change in this free fall acceleration as you climb a mountain, well, that would be g minus g naught, right? It's your final value of g minus what you would have for g at the surface. Take this expression for g and subtract g naught, and you're just left with the second term, -2h over r times g naught. So if I want the fractional change, so the change in g compared to g naught, of course, you could turn that into a percent change by multiplying by 100. just take delta G and divide by G naught. So the G naught goes away, and it's just negative 2H over R. And I don't have that memorized. I kind of wish I did because it's pretty useful. You could even use it for something like just going to the top of a tall building. If you knew the height of the tallest building on the LBCC campus, or even just the D building. If you knew the height of the D building, you could plug that height in, divide it by the radius of the Earth, multiply by 2, and that would tell you the fractional change in G. In fact, I could estimate that. Let's see, there's 3, we're on the 3rd floor, so that's up 2 flights, and then you got to get to the roof. So I don't know, what is it, 4 times 4? Maybe it's 16 meters. That's super approximate. So if I take 16 meters and divide it by the radius of the Earth, which is basically 6,400 kilometers, multiply by 2. Okay, the fractional change is 5 parts per million. That's 10 to the negative 6th. Okay, so the strength of the G field is smaller by 5 parts per million when you go to the top of the D building. And that's why you don't really notice it. You don't feel noticeably lighter on the top of the D building, unless you happen to be standing near the vents for the chemistry department, because I don't know what you're inhaling at that point. But for this problem, let's see if we can use this approximation to corroborate what we got using the more exact expression here. So now that we know the height, let's find the change in G. Remember the statement of the problem in the book, at least, you guys have different numbers in mastering, was that G was 0.0075 meters per second squared less. That would be the delta G. In the problem, delta G was 0.0075. So let's go ahead and plug in the numbers that we now know. For 1310, delta G was -2 times the height of, well, we just found that 2.4 kilometers was that mountaintop observatory, and then I'll go with 6,400 roughly kilometers, and then G naught, of course, is 9.83 meters per second squared. So what's the amount by which G changes using the binomial approximation? You don't need to know the binomial approximation for your exam. It's just a fun little extra here, times 9.83. And there it is, excuse me, 0.0073. Okay, so not 0.0075, there's some error there. And again, that's because the binomial approximation is just that, it's an approximation. Yeah? Okay, one more little fun with numbers exercise. If you take the year 2020 and you divide it by 666, let's see, what do we get here? 2020 divided by 666, 3.0330. If you leave off the decimal point, that's just 30330. Any significance to that? I don't know.